Find the area enclosed by the loop. In the curve x equals t squared, y equals t cubed minus 2t. All right, so let's first look at the graph. Y equals t squared, y equals t cubed minus 3t. Plug that in. All right, now, with my parameters, just to make a note here, I've got t min 0, t max 2 pi. And I do that, what it's showing me is not a full picture here. Because there is a loop here. And so what that means, usually what that means is I need to go back a little bit. Instead of 0, I need that to be negative 2 pi. So if you don't see your loop, just play around with the min and the max. Let's go to negative 2 pi to 2 pi. There we go. All right, so if I do that, then here we go. Then it comes up like this and then goes around. So I want to find the area here enclosed by this loop. So it's basically from start right here, get all that area, and then that area as well. That's what I want to find. Okay, well, what I notice here is that the loop is closed where it's right here on the x-axis, or the closing, if you will, happens when I have an x-intercept to another x-intercept, because it loops around like this. So from x-intercept to x-intercept, or this x-intercept to that x-intercept. So I need to figure out what that x-intercept is. Well, to find an x-intercept, that's y equals 0. I need to know where, for this function, I've got y equals 0. Well, I've got a y equation there. Let's just set y equals 0. Well, that solves out pretty nicely. Factor off the t equals 0, t squared minus 2 equals 0. So this would give me t is plus or minus square root of 2, wouldn't it? Now, it's pretty clear at t equals 0, that's not what I'm interested in, because at t equals 0, it's x is 0, y is 0, so that's this point. I want the other 2 points, so that's when t is square root of 2 and t equals negative square root of 2. When it's coming in here at negative square, and you can check it, trace it on your graph there, at negative square root of 2, it first crosses the x-axis there, and then it comes on around, and then at positive square root of 2, it's going to cross it again. What does that mean? I want to know then the area that is swept out between t equals square root of 2 and t equals negative square root of 2. Sorry, negative square root of 2 to positive square root of 2. Let's do it the right order here. Usually the way we operate. So I want to find that area that's swept when I start at t equals square root of 2, negative square root of 2, and then when it sweeps on around to where it's positive square root of 2, because it's going like this, I want to find that area that's swept out, and that's where I use then my formula. Area equals, it's g of t times f prime of t dt, alpha to beta, which in this case I found out. Alpha and beta is negative square root of 2 to positive square root of 2. Okay? All right, so what do I get here in this case? So it's the integral, negative square root of 2 to positive square root of 2. The g of t of the y, 3t squared, t cubed minus 2t, times f prime, which is the x, which would be 2t. X prime or f prime is 2t. 2t. dt. This is the integral I need to know about right there. Well, it's a lot nicer one than we had previous. All I have to do here, right, is multiply that out. 2t times that would be 2t to the fourth. 2t times minus 2t is minus 4t squared. And then it's just antiderivative. All right, so that would be, what, 2/5 t to the fifth minus 4/3 t to the third. And I'm going to go from negative square root of 2 to positive square root of 2. And that'll find my lovely little area. And so that would be 2/5 square root of 2 to the fifth minus 4/3 square root of 2 cubed minus, plug in the negative square root of 2, so it'll be 2/5 times minus square root of 2 to the fifth minus 4/3 square root of 2 to the third. Negative square root of 2 to the third. All right. Well, as far as simplifying this, square root of 2 to the fifth, well, you got square root of 2 squared, square root of 2 squared, that'd be the fourth, and then another square root of 2. So that's 2, that's 2, that's square root of 2. So that's 4 square root of 2. So here I have a is 2/5. That would be 4 square root of 2. Square root of 2 cubed, well, that's square root of 2 squared, square root of 2. So that would be minus 4/3. Square root of 2 is 2, square root of 2. Minus, that would be a negative. Same thing here, negative 4. Square root of 2 is what that would be. So that'd be 2/5. Negative 2/5, that'll be a positive. Well, let's just do it this way. So, got another step anyway. 2/5 times negative 4 square root of 2. And negative 2 cubed, that would be negative 2 square root of 2. So that would be negative times that would be positive 8/3 square root of 2. Something like that. All right, so I've got 8/5 square root of 2 minus 8/3 square root of 2. Minus and minus will be a plus 8/5 square root of 2. Minus and minus will be minus 8/3 square root of 2. Yeah, it's doubling basically. So I've got 8/5 and 8/5. That would be 16/5 square root of 2 minus 16/3 square root of 2 if you want the nice, lovely exact value there. And if you got a common denominator, you can simplify it on down. I think it works out to be 15ths there. All right. Okay. Well, the other, so that's the area swept out. Let's talk about arc length here. Compare it to what we found out about arc length previously. Arc length of parametric curves. Well, we know that if we're in the Cartesian setting, y equals f of x from the arc length from A to B, is, well, it's the L equals, it's the integral of a to b, 1 plus f prime of x squared dx. Or to put it another way, that is dy dx squared or to put it another way, if we're in parametric, all right, so if we've got a parametric setting, then x equals f of t, y equals g of t, then we know that dy dx, that's dy dt over dx dt right there. And that would be squared. Well, if we get, okay, and then what about, so now I've changed over to parametric, so I need to get this in terms of t dx. I remember dx was, well, it was f prime of t dt. And then I go from now, instead of x equals a to b, now I'm going to go from t is alpha to beta. All right? Okay, well, to make this look a little better, that would certainly work, but to make it look a little bit better, it works out pretty nicely if we get a common denominator here, which would be dx dt squared. And if I multiply the well, let's change this. Here's what we're going to do. Here's how we get the nice form of this. Take this and rewrite that. Couldn't I rewrite that as dx dt? That's the same thing as that. Okay, so I have L equals alpha to beta, square root of 1 plus dy dt squared. I mean dy dt over dx dt squared. And that's dx dt. But here's a really smooth little trick, because can I write that as the square root of dx dt squared? This is one way we can look at this. And then if I multiply that on the inside, it may look like an awful mess, but if I multiply, because it's into the square roots, I can do this. This, the square root of dx dt squared times 1 is, of course, dx dt squared. Plus, now, that's dx dy dt squared over dx dt squared. So if I multiply it by dx dt squared, notice that the dx dt squareds cancel, so I have just dy dt squared. dt. This is the preferred form here, basically because what this is saying, to get, this is arc length for parametric, to get the arc length for parametric equations, x equals f of t, y equals g of t, the arc length is equal to the integral from alpha to beta, from t equals alpha to t equals beta. You take the square root of dx dt, so you take the derivative of that, plus the derivative of the y, dy dt, squared it, dt. Or you can put it in those exact terms if you want to. F prime of t squared plus g prime of t squared. Either one. All right. Let's do one. Finish out with that. Find the arc length using parametric equations. Specifically these. Okay? Find the length of the curve. X equals cosine cubed t. Y equals sine cubed t, where t is going to go from 0 to pi over 2. All right. So there's my little formula there. L equals the integral from alpha to beta, square root of, I think the book likes dx dt squared, plus dy dt squared, so I'll go with that, dt. And so what I need is I need dx dt and dy dt. Well, dx dt is just the derivative of cosine cubed t, which is cosine t cubed, which is a chain rule. So that'd be 3 cosine t squared times the derivative of the inside would be negative sine t. That's dx dt squared, and then we're going to square it. I also need dy dt. Well, similar thing for y. That's sine t cubed. So the derivative of it would be 3 sine t squared times the derivative of the inside would be cosine. So I plug those in. Here's what I get. The arc length is alpha to beta, so I'm going alpha to beta, 0 to pi over 2. Square root of, well, dx dt squared, so I'd take 3 cosine squared t negative sine t. Square that. Don't forget you got to square it. Plus then dy dt, which is 3 sine squared t cosine t squared. And then dt. Which looks like, again, an awful mess, but I think some nice things are going to happen. All right, so let's square those out. 0 to pi over 2. That'll be 9. Square that, you get cosine to the 4th. Sine squared. Same thing basically out of 9. Sine to the 4th t cosine squared t dt. That's my interval. Which looks bad, but let's see. I do have some nice common factors. Apparently that's why they chose these. All right. I've got a 9 common factor. They both have cosine squared in them, and they both have sine squared. So let's factor those out. So I have this 9, what did I say, cosine squared and sine squared. Can factor those out. That'll leave me, what, cosine squared, t, out of that. Both of those others are gone. And then 9 sine squared, so there's still a sine squared there. Cosine squared is gone. So I think this is what I get. Well, even something nicer happens here. Cosine squared plus sine squared, what about that? That's 1. So wind up just having the square root of 9 cosine squared sine squared, but I can square root those. Isn't that the integral? 0 to pi over 2. Square root of 9 is 3. Square root of cosine squared is cosine. Square root of sine squared is sine. We'll wind up with just this nice, neat, lovely little thing. All right, so again, our trig integrals, sine t, cosine t. How do we do that one? It's just a sneaky little u substitution. If we let u equal sine of t, then du would be cosine of t dt. So divide cosine t off. That's what we're going for dt. So L equals the integral 3 cosine t. I'll let sine t be the u. dt is du over cosine t. Works out because now it's just 3u du. That's just 3 times 1/2 u squared. But the u is sine, so it's 1/2 of sine t squared. 0 to pi over 2. Okay? Which, if I plug that in, I'll have 3/2 sine of t sine of pi over 2 squared minus 3/2 sine of 0 squared. But that's pretty nice because the sine of 0 is just 0. So it's 3/2 times the sine of pi over 2 squared. Pi over 2, the sine of it, it's 1. So I have 3/2 times 1 squared, that's 3/2. So this works out actually to be a nice little arc length right there.